Hello. This is a rather belated talk on the advanced features of Simple V, focusing mostly on data-dependent fail first. Many thanks to Genon for funding this NGI sure. The basics of Simple V you can see from many other talks that have done is effectively a loop where usually each element, or in most cases each element, like SIMD hardware, is independent of each other. But that's not necessarily the case. You can see from this condition register destination BA plus ID is the comparison of a GPR against an assigned immediate. If you're familiar with the power ISO compile, it's basically the compile instruction wrapped, but you can see that the source and the destination are optionally incremented by 1 on each time round the loop, and so the hardware can very easily choose, if it wants to parallelize that as much as it likes. The key thing about Simple V is that it is left up to the implementer of the hardware to choose the level of parallelism, where normally with SIMD it is assumed that the hardware is directly, you're 128-bit wide, therefore the hardware is going to be 128-bit wide. Yes, it's not the case with Simple V. It is up to the hardware implementer, right? Simple V is a specification which makes programming easier, right? So, very much oversimplified, predication, element width overrides, all left out. But you can see that scalar, and scalar vector, and vector vector, and vector scalar are all combined into one thing. And yeah, object-oriented out of order, our microarchitecture may choose to push multiple compiles into an instruction queue, making it very, very busy. It can easily saturate the back end, and this sits idle. So that's the basics. Right? But every single operation is parallelized in a RISC paradigm prefix fashion, generical fashion. So now, going straight onto the thing, you've got a concept called load store fault first. Right, this is one that is implemented in ARM SVE and also in RISC-V vectors. Basically, the problem is that your vector load and store could create a page fault, which is particularly bad, either on a misaligned boundary or at the end of a virtual memory page. Now, if you want your instruction to be atomic, that puts a serious burden on your hardware, because you have to do a TLB miss and lookup across a page boundary, which could really make things very, very difficult. So a solution is a protocol which allows for optional load and store. It's a contract. The instruction requests up to a certain number of elements, minimum of 1, and the instruction informs the programmer via some form of API of how many were actually loaded. The first element in the load store is not optional. It cannot fail or be truncated, and so this first element must trigger a page fault or a virtual memory or whatever kind of standard fault, as if it was a scalar load. Okay, alright, so there's more on the Wikipedia vector processor page on fault-fail first. Okay, right, now, so that's a well-established concept. You can look it up online on papers from 2019. Alright, where load store is memory to or from a register, what about register to register? Why don't we have the similar contract? Hey guys, do this, I would like you to do up to this much, but tell me if there is a condition which fails where you truncate the vector length and tell me how many you actually did. And that we call data dependent fail first. And it turns out that the Zilog Z80 from several decades ago has this already. It's called the LDIR instruction for memory to register and the CPIR instruction for register to register. Okay? Alright, so this is not a new concept. Data dependent fail first is not a new concept. Just extended it. Right? So, the bit that's new is this test. If you test the result, the condition register which you just did in the compare, if it fails, you set the vector length equal to the current point length of where you got up to, and you stop. Or you set it equal to the inclusive or exclusive of depending on which one you want. And I added the option to do that so that you could include or exclude a null pointer, a string end of character, or a saturation overflow in floating point, for example. Alright, and what that means is that you can keep in a saturated audio thing, you can keep the inner loop pure, and you can test after the running the loop if there was a failure, or you can exit the loop testing the condition of a saturation failure. And if that happens, you can jump to somewhere which will handle the saturation event for audio clipping or change the volume or whatever it is, but you don't poison the inner loop with unnecessary saturation testing and truncation and this and that and anything and bullshit. Very simple bullshit. Right? So, the important thing you'll note here is that parallelism is still perfectly possible. In an out-of-order microarchitecture, you have speculative execution, and what you do is you hold off writing the results back until you do a sequential post-analysis of the operations that had just been carried out in parallel. And the thing is that the post-analysis test is just a bit test. You can do that in parallel, and you can use find longest run of ones. So you have 1 1 1 1 0 1 1 1. Well, that's 1 1 1 1. So you truncate a 4. It doesn't matter what if there's any other ones or zeros after that first 0. You don't care about those. You only care about where you got up to sequentially in the thing. But so what you do is, because you've got a shadow hold in outer order of all the results, the fourth one you clear the thing and allow them to write to the register file, and you cancel 5 and above. It's real simple, and this out of order microarchitecture, this is standard stuff. So we're just simply hooking directly in to standard out of order microarchitecture designs, which are already parallel. So it ain't rocket science, guys. Alright, so Psi. The irony is, in Power ISA v3.1 they've added this instruction vstra IBR, and it is identical to data dependent fail first, but it's hard coded and can only be used for exactly the purpose of the thing. You can't apply it like you can in simple V. You can apply data dependent fail first to every single instruction, not just one hard coded one. Yeah, which is VSX only. This is VSX only. Or what if I want something in the scalar registers? Yeah, GPRs or FPRs. You can't. Alright, so let's do some quick demos of these things. So first one we're going to do is positional pop count. Now, you can see from the pseudocode here that it is the wrong way round. This is the way that you normally do pop count. You count the number of ones in the bits, and that becomes your result. If you've got an array of them, you end up with counting them that way. Alright? But positional pop count counts downwards. It counts all of the LSBs. Bit 0 counts all of bit 1, counts all of bit 2 to how many you have. Okay, so it's the other way around, and unfortunately, yeah, the challenge is to transpose the data, to flip these, so that you can do them in blocks. Now, it turns out that we added the GBBD instruction, which is in draft, is based on VGBBD, which does a transpose in a 64-bit, trace it as an 8x8 block, and just mirrors the whole lot about the diagonal. Alright, so real simple. So we use that here. Now this sv.lbzu with post increment is a new instruction which avoids us having to do a pre-decrement outside of the loop. To do the load, but also we have a destination which equals 8 as an override on element with override on that, and because it is an update and it's a loop, and that R4 there, we can see the cursor, R4 there is a scalar, it will continuously update, so it will overwrite, and the last winner will be the last address which can be used on the next time round the loop. Alright, so we set the vector length to 8 here. Alright, line 2. Alright, then we load 8 elements, okay, which gives you your 64 bits, and then we do that transpose as a single scalar instruction. Now they're turned around, we can do a pop count on those things, producing 8 results. We can add them to an accumulator, but notice how it says source width equals 8, but the destination width is left as 64, the default. So it does a pop count of 8-bit values, placing them automatically, doing a sign extension, a 0 extension to 64-bit, and then performing the SV and adding on those into accumulating of the 8 results. And then we're doing a CTR loop, so it branches back and does the next batch. It's so simple, and it's parallelizable. Yeah. Now, if you wanted more details on that, then there's the page. Where is it? Yeah, here we go. That page. There's the full write up there on the pop count. Now, Stronocopy looks real simple. Alright? Looks incredibly simple. Oh, just copy the destination, source to the destination for up to n, and then put 0 characters in the end. The tricky bit is this data dependence, where you're testing the source for not being a null character, and data dependent fail first is perfect for that. Performs parallel loads and conditionally stops on the first detection of a sequential detection of a 0. It's so simple. And then from that point onwards we go into the rest of the loop and we pad it out with zeros until the end. Now, we produce a vector of CRs, condition register, which we test with the SV.BC all instruction. Okay, alright, so that's effectively that's the end, alright, which effectively decrements the counter by the vector length. But it does so by counting. Okay? Alright? Oh, yeah, stop it like that. Yeah, alright. So, first thing we set the vector length to 64, so we're doing 64 bytes at a time. Alright? So, huge numbers of things to load, huge numbers, let's say 8 bytes. It could easily be more, but we'd actually start to run out of registers. So we've only got 128 registers, but bear in mind, a multi-issue out-of-order microarchitecture can issue multiple simple V instructions simultaneously per clock, where each of those instructions can do multiple elements per clock as well, and you can do back-end merging, etc., etc. So the opportunities for parallelism are massive. Anyway, so we've already explained the LBZU post increment. Alright, so the R10 address will end up with the last winner of being overwritten, because it's a scalar, which means that it will be the starting point for on the next loop around L1. The compy is the fail first, but we want it inclusive because we want to include the null terminating character. Okay? And it chops the length at the end of VL. So the *0 stores a vector of condition registers in the EQ bit, I think. Right? So then, because VL has been chopped at including the null character, we do a store at the destination, and again, register 12, the destination address gets updated and has the last thing. Now, we continued looping if there weren't any fails. Okay, so we're testing all of the EQ bits to check that they weren't zero, and stop at the one that does. But each time it goes round this loop, it will decrement CTR, and importantly, terminate when CTR is zero. Right? Okay. So, and then we do the zero looping, which is basically the same thing. We do the store of a 0, and that's why we've got this extra instruction add I000, because we're storing 0 in address 12, updating it each time, and we branch conditional back to the thing. So it's incredibly simple and parallelizable. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions. I mean, horrendously parallelizable 10 instructions. Alright, so, yeah. Now, this next one is linked list walking. Alright, so we start with register 10 pointing to address 0x0107. Right, and it's a fail first on testing of whether RC1 is a shorthand for please test if it's non-zero, and if it's 0, stop. But the VLI says stop including the null. So basically we're getting the addresses of each element in our linked list. We're getting the addresses of each element in our linked list, terminating at the null character. Okay, so LBZ but he will update register 10 continuously and at the end, it will fail at the contents where where register 10 will end up being 0.001.009, and the VL is truncated to 5, not 4, because it is HELL. 1, 2, 3, 4. HELO. 10, 16, 17. So I might have got that wrong. It might have been truncated to 4, not 3. Whoops. Oh, I'm not redoing the talk just because of that. So we just have to take us through, okay? Moving swiftly on. Fine. Right, so the linked list walking, alright, is a little more involved, but it's basically the same thing. Where this one you can see up here, the instruction 1 brackets 10 is a scalar, so register 10 will end up pointing to the no, it won't end up, it won't get modified because it's not LBZU. It will, register 16 will contain just the HEL, and the 16, 17, 18, 19 will contain the HELO of 1007 plus 1, 8 plus 1, 9 plus 1, 10. Ah, I really messed that up, didn't I? That should have been 0x10, 0A. Whoops. I'll edit that later. Moving swiftly on. Alright. Now by contrast here, the star 16 is the address is a vector as well, and it's very important to note that the destination where you're loading is 1 greater than the source where you're loading from. So you're storing in register 17 and loading from 16, and then on the next time round the loop you load from 17 and store in 18. On the next time round the loop you load from 18 and store in 19. On the next time round 19, 20, 20, 21, 21, 22, etc, etc, depending on the vector length. Alright, so we start with register 16 equal to 24. Okay, alright, and what gets loaded is the register 17 gets 24 plus 8. There we go. Effective equals 32. Effective address 1. Alright? And so 17 gets set to 48. Now on the next time round the loop, we're going to load from 0. So this goes 16, 17, 18, 19, and the destination goes 17, 18, 19, 20. Alright? So you can see, you can just do the exercise for yourself. Follow the arrows. Plus 8, 24 plus 8, 48. Go to address 48 on the next instance. 48 plus 8 is 56. Load from that is 8. That goes into register 18. Register 18, on the next load, you add 8, you've got address 80. From 80 you add 8, and it's 88 and you have a 0. And when you find that 0, that of course fails, because it's 0. Fail first, RC1, it has to be non-zero. Tilde RC1 means it has to be 0, but it's kind of, well, I can see there'll be uses for it. You would want to test a run of all zeros and find the point in memory where the first non-zero was. Yeah? Alright, so you'll be able to search for non-zero with a single instruction. Yeah? Right. So, but in this case we want to include that null, so R20 gets set to 0 and the vector length gets set to 5. Now that's a linked list walking in one instruction. It's ridiculously powerful. Max lock. Max lock is notoriously difficult. Alright. Most algorithms are depth first, recursive descent in a map reduced style. So you have to have a stack. It's yeah, horribly complex. And once you've got down to the leaf nodes, you then have to offset the locally computed largest index to where you are in your tree, and you have to record the index and the value, reconstruct a new array to pass to your SIMD hardware to test recurse back. It's horrible. Alright? Whereas SV64 is a simple data dependent fail first loop. Alright? The first while loop is literally sv.com. You're doing an sv.com against m as a scalar. So you're doing a vector compare it against a scalar. And the data dependent fail first truncates at the first comp that matches. You've done that entire while loop in one instruction. Right. The next one is a little bit more complex, but it's basically sv.min-max, which is a new draft instruction that we're adding. And then there's a CR NAND, it's SVCR NAND. Here we go, an sv.cr NAND, which that mask, that m equals lt here, with zeroing. Basically what that does is it effectively treats the vector predicate as if it was a third operand, turning what would normally be a 2-in 1-out instruction into a 3-in 1-out instruction, which is limited to basically ANDing, or ANDing with inversion in this particular case, because you can masking, you're allowed to invert the predicate mask. All right, so it's best to see the full page for details. Here it is at the bottom of this one. It's the Fortran Maxlock page in the cookbook, and there's quite a lot of housekeeping. But yeah, it's quite straightforward, but just a little bit involved. But there's only 10 instructions. See? Right. So it really is massive compactification of ISAs in general. Right? Simple V is a general concept, an abstract risk paradigm concept that could be applied to any ISA. So, summary. SIMD and SIMD instruction sets fundamentally assumes element independence. If the elements are not independent, you're really screwed. You had to power ISA 3.1, had to add that one instruction which is non-independent. Z80, CPIR and LDIR have had data dependent fail first in concept for literally over 50 years. Right. There's no provision in SIMD ISAs or architectures for inter-element interdependence, let alone sequential interdependence. Alright? And it gets really tricky. Right? If there is any provision, it's limited to a few targeted specific instructions, such as that Vestry one. Yeah? Right. Well, Simple V adds to data dependent fail first as a general risk paradigm concept, exploiting the production of condition registers. So you use it with RC equals 1. Or if you don't have RC equals 1, you can implicitly do a test for 0 or non-zero. Alright. Hardware parallelism is still possible, as I explained earlier. You produce the results in parallel. You hold off writing those parallel results. You post-analyze them using a very simple piece of hardware, which is find the longest run of of ones, right? And from that you cancel results that should not be written, but you're using existing standard, industry standard, out of order microarchitecture to just ride on the back of it. And the result is a huge simplification of algorithms, massive compactification of your things, just like it's at Zilog Z80 and MT86 with their rep instructions. It's still parallel. And you end up with this compact, deep expressive assembler, which gives you CISC capability, but with a RISC paradigm prefix on top of a RISC ISA suffix. You do not need any SIMD instructions, because that remains at the back end in the hardware where it belongs, not exposed directly at the programmer and expecting them to like it. Yeah, so this is a big damn deal like this. Okay, so thank you very much. Those are links of everything that we've got. Really appreciate your time.